Designing plastic parts is a complex task involving many factors that addresses a list of requirements of the application. How is the part to be used? How does it fit to other parts in the assembly? What loads will it experience in use? In addition to functional and structural issues, processing issues plays a large role in the design of injection molded plastic part. How the molten plastic enters, fills, and cools within the cavity to form the part largely drives what form the features in the part must take. Dividing a part into basic groups will help you to build part in a logical manner while minimizing molding problems. As a part is developed, always keep in mind how the part is molded and what you can do to minimize the stress. Applications. Plastic injection molding is the preferred process for manufacturing of plastic parts. Injection molding is used to create many things such as electronic housings, containers, bottles, automotive interiors, and most of the other plastic products available today. It is ideal for producing high volumes of plastic parts due to the fact that several parts can be produced in each cycle by using multi-cavity injection molds. Some advantages of injection molding are high tolerance precision, repeatability, large material selection, low labor cost, minimal scrap losses, and little need to finish the part after molding. Some disadvantages of these processes are expensive upfront tooling investment and process limitation. Polymers for injection molding. Most polymers may be used, including all thermoplastics and some elastomers. There are tens of thousands of different materials available for injection molding. Product designers can choose from vast selection of materials to find the one that has exactly the right properties. Materials are chosen based on the strength and function required for the final part. But also each material has different parameters for molding that must be considered. Common polymers like nylon, polyethylene, and polystyrene are thermoplastic. Mold. The mold or die refers to the tooling used to produce plastic parts in molding. Traditionally, injection molds have been expensive to manufacture and were only used in high-volume production applications where thousands of parts were produced. Molds are typically constructed from hardened steel, pre-hardened steel, aluminum, and beryllium copper alloy. Steel molds generally cost more to construct but offer longer lifespan that will offset the higher initial cost over the higher number of parts made before the wearing out. Pre-hardened steel molds are less wear resistant and primarily used for lower volume requirements or larger components. The hardness of pre-hardened steel measure typically 38 to 45 on Rockwell C scale. Hardened steel molds are heated after machining, making them superior in terms of wear resistance and lifespan. Typical hardness ranges between 50 and 60 Rockwell C. Aluminum molds cost substantially less than steel molds, and when higher grade aluminum such as QC7 and QC10 aircraft aluminum is used and machined with modern computerized equipment, they can be economical for molding hundreds of thousands of parts. Aluminum molds also offer quick turnaround and faster cycle because of better heat dissipation. They can also be coated for wear resistance to fiberglass reinforced materials. Beryllium copper is used in areas where mold which require a fast heat removal or areas that see the most shear heat generated. Injection molding process. With injection molding, granular plastic is fed by a hopper into heated barrel. As the granules are slowly pushed forward by screw-type plunger, the plastic is forced into heated chamber called the barrel, where it is melted. As the plunger advances, the melted plastic forced through a nozzle that sits against the mold's sprue bushing, allowing it to enter mold cavity through a gate and runner system. The mold remains at the set temperature so the plastic can solidify as soon as mold is filled. Injection molding cycle. The sequence of events during the injection molding of plastic part is called the injection molding cycle. The cycle begins when the mold closes, followed by the injection of polymer into the mold cavity. Once the cavity is filled, a holding pressure is maintained to compensate for the material shrinkage. In the next step, the screw turns, feeding the next shot to the front screw. This causes the screw to retract as the next shot is prepared. Once the part is sufficiently cooled, the mold opens and the part is ejected. Different types of injection molding processes. There are different types of injection molding processes available, like co-injection molding, fusible core injection molding, gas-assisted injection molding, in-mold decoration and in-mold lamination, injection compression molding, injection molding of liquid silicone rubber, insert and outsert molding, micro-layer injection molding, low-pressure injection molding, micro-injection molding, microcellular molding, multi-component injection molding, multiple live fluid injection molding, powder injection molding, push-pull injection molding, reaction injection molding, resin transfer molding, reho molding, structural foam injection molding, structural reaction injection molding, thin wall molding, vibration gas injection molding, water assisted injection molding, rubber injection molding. Stress. The main enemy of injection molded parts is stress. When plastic resin is melted in preparation for molding, the molecular bonds are temporarily broken due to the heat and the shear force of the extruder, allowing the molecules to flow into the mold. Using pressure, the resin is forced into mold, filling every feature, crack and crevice of the mold. As the molecules are pushed through each feature, they are forced to bend, turn and distort to form the shape of the part. Turning hard to sharp corners exerts more stress on the molecule than taking gentle turns with generous radius. As the material cools and molecular bond reeling the resin into the rigid form, these stresses are in effect locked into the part. Part stresses can cause warpage, sink marks, cracking, premature failure, and other problems. While some stresses in an injection molded parts are to be expected, you should design your parts with as much as consideration for stress reduction as possible. Some ways to do this by adding smooth transition between features and using round and fillets in possible high stress areas. Gates. Each injection mold design must have a gate, or an opening that allows the molten plastic to be injected into the cavity of the mold. Gate type, design, and location can have effects on the part, such as part packing, gate removal, cosmetic appearance of the part, and part dimension and warping. Gate types. There are two types of gates available in injection molding: manually trimmed and automatically trimmed gates. Manually trimmed gates. These types of gates required an operator to separate the parts from the runners manually after each cycle. Manually trimmed gates are chosen for several reasons. The gate is too bulky to be automatically shredded by the machine. Shear sensitive materials such as PVC cannot be exposed to higher shear rates. Flow distribution for certain designs that require simultaneous flow distribution across a wide front. Automatically trimmed gates. These types of gates incorporate features in the tool to break or shear the gates when the tool opens to eject the part. Automatically trimmed gates are used for several reasons: avoiding gate removal as the secondary operation, reducing the cost, maintaining consistent cycle times for all parts, minimizing gate scars on the parts. Common gate design. The largest factor to consider when choosing the proper gate type for your application is the gate design. There are many different gate designs available based on the size and shape of your part. Below are 4 most popular gate designs used by quick parts customers. The edge gate. The edge gate is the most common gate design. As the name indicates, this gate is located on the edge of the part and it is best suited for the flat parts. Edge gates are ideal for medium and thick sections and can be used on multi-cavity two-plate tools. This gate will leave a scar at the parting line. The sub gate. The sub gate is the only automatically trimmed gate on the list. Ejector pins will be necessary for the automatic trimming of this gate. Sub gates are quite common and have several variations such as banana gate, tunnel gate and smiley gate, to name a few. The sub gate allows you to get away from the parting line, giving more flexibility to place the gate at optimum location of the part. This gate leaves a pin-sized scar on the part. The hot tip gate. The hot tip gate is the most common of all hot runner gates. Hot tip gates are typically located at the top of the part rather than on parting line and are ideal for round or conical shapes where a uniform flow is necessary. This gate leaves small raised knob on the surface of the part. Hot tip gates are only used with hot runners molding systems. This means that unlike the cold runner systems, the plastic is ejected into mold through heated nozzle and then cooled to the proper thickness and shape in the mold. Direct or sprue gate. Direct or sprue gate is manually trimmed gate that is used in single cavity molds of large cylindrical parts that require symmetrical filling. Direct gates are easiest to design and have low cost and low maintenance requirements. Direct gated parts are typically lower stressed and provide high strength. This gate leaves large scar on the part at the point of the contact. Gate location. To avoid problems from your gate location, here are some guidelines for choosing the proper gate location. Place gate at the heaviest cross section to allow part packing and minimize voids and sink. Minimize obstruction in the flow path by placing gates away from the cores and pins. Be sure that stress from the gate is in area that will not affect the part function or aesthetics. If you are using the plastic with high shrinkage grade, the part may shrink near the gate, causing the gate pucker if there is high molded in stress at the gate. Be sure to allow the easy manual or automatic degating. Gate should minimize flow path length to avoid cosmetic flow marks. In some cases, it may be necessary to add second gate to properly fill the parts. If filling problems occur with the thin wall parts, add flow channels or make wall thickness adjustment to correct the flow. Gates vary in size and shapes depending upon the type of plastic being molded and the size of the part. Large parts required larger gates to provide a bigger flow of resin to shorten the mold time. Small gates have better appearance but take longer time to mold or may need to have higher pressure to fill correctly. Wall thickness. After ejection from the mold, injection molded parts are cooled down from manufacturing temperatures so that they can hold their shape when ejected. During the part cooling step of the molding process, change in pressure, velocity and plastic viscosity should be minimized to avoid the defects. Few aspects are more crucial during this period than wall thickness. This feature can have major effects on the cost, production, speed and quality of the final parts. Proper wall thickness. Choosing the proper wall thickness for your part can have drastic effects on the cost and production speed of the manufacturing. While there are no wall thickness restrictions, the goal is to choose thinnest wall possible. Thinner walls use less material, which reduces the cost and takes less time to cool, reducing the cycle time. The minimum wall thickness that can be used depend on the size of the geometry of the part and structural requirements and flow behavior of the resin. The wall thickness of an injection molded part generally range from 2 mm to 4 mm. Thin wall injection molding can produce walls as thin as 0.5 mm. This chart shows recommended wall thickness for common injection molding resins. Uniform wall thickness. Thick section takes longer to cool than thin ones. During the cooling process, if walls have inconsistent thickness, the thinner walls will cool first while the thick walls are still solidifying. As the thick section cools, it shrinks around the already solid thinner sections. This causes warping, twisting, and cracking to occur where two sections meet. To avoid this problem, try to design with completely uniform wall throughout the part. When uniform walls are not possible, then change in thickness should be as gradual as possible. Wall thickness variation should not exceed 10% in high mold shrinkage plastics. Thickness transition should be made gradually or in order of 3 to 1. This gradual transition avoids stress concentrations and abrupt cooling differences. If your part is so complex that you need variations on your wall thickness, look for an alternative. You may want to design features such as coring or using ribs. At the very least, try not to make transition between thicker and thinner sections too abrupt. Try using gradual transitions or chamfered corners to minimize the dramatic change in pressure inside the mold. Draft. Most injection molded plastic parts include features such as outside walls and internal ribs that are formed by opposing surfaces of tool metal inside the closed mold. To properly release the part when mold opens, the side walls of the mold are tapered in the direction that the mold opens. This tapering is referred to as draft in the line of draw. This draft allows the part to break free of the mold as soon as the mold opens. The amount of draft required can be depend on surface finish of the mold. A smooth, polished tool surface will allow the part to eject with less draft than standard tool surface. The amount of draft required will vary with geometry and surface texture requirements of the parts. Here are some rules for using draft properly. Be sure to add draft to your 3D CAD model before creating radius. Use at least 1 degree of draft on all vertical faces. 1.5 degrees of draft is required for light textures. 2 degrees of draft works well in most situations. 3 degrees of draft is required for medium texture. Sink marks. When the hot melt flows into the injection mold, the thick sections don't cool as fast as rest of the part because the thicker material becomes insulated by the outside surface of faster cooling plastic. As the inner core cools, it shrinks at different rate than the already cooled outer skin. This difference on cooling rates causes the thick section to draw inward and create sink mark on the outside surface of the part, or worse, completely warp the part. In addition to being unattractive, the mark also represents added stress that builds into the part. Other less conspicuous areas where sink occurs include ribs, bosses, and corners. These are often overlooked because neither the feature nor the part itself is too thick. However, the intersection of two can be the problem. One way to avoid sink mark is to core out the solid section of the part to reduce the thick areas. If the strength of the solid part is required, try using cross-hatched rib pattern inside the cored out areas to increase the strength and avoid the sink. As rule of thumb, make sure that all bosses and locating and support ribs are no more than 60% of the thickness of the nominal wall. Textures. Texturing is the process used to apply patterns to the mold surface. This process allows flexibility in creating the final appearance of the parts. Texturing is an integral piece in overall product development and should be considered during the part design process to achieve the desired results. Textures can be functional component of design as well. Imperfect parts can be hidden by the right texture. Textures can be used to hide fingerprints and improve the grip for the end user. Textures can also be used to reduce part wear from the friction. A wide variety of textures are available for injection molded parts such as natural or exotic textures, matte finish textures, multi-gloss patterns, fusions, graphics, leather grains, wood grains, geometric lines, images or logos incorporate into the pattern. When applying a texture to the part, the CAD drawing must be adjusted to accommodate for this surface variance. If the texture is on the surface that is perpendicular or angled away from the mold opening, then no draft changes are necessary. If the texture is on parallel surface with the mold opening, however, increased draft is necessary to prevent scraping and drag marks that could occur during the part ejection. Different textures have different impacts on the molded parts. The rule of thumb when designing for texture is to have 1.5 degrees of draft for each micron of the texture finish depth. Parting lines. A parting line is the line of separation on the part where two halves of the mold meet. The line actually indicates the parting plane that passes through the part. While on simple parts, this plane can be simple flat surface, it is often complex form that traces the perimeter of the part around the various features that makes up the part's outer silhouette. Part lines can also occur where any two pieces of the mold meet. This can include the side action pins, tool inserts, and shutoffs. Parting lines cannot be avoided. Every part has them. Keep in mind while designing your part that the melt will always flow towards the parting line because it is the easiest place for the displaced air to escape or vent.